In this video, what we'll be doing is we'll again try to obtain this Heisenberg's uncertainty principle using single slit diffraction experiment. And in doing so, what should I do is that I would like to have a narrow slit. I would like to have a narrow slit. Let us assume that we have a slit here. And of course, this slit has to be extremely small, of the order of wavelength of light. Uh, and this slit is, let me assume that this slit has a width equal to delta x. And let us assume that a collimated beam of electrons travel through this slit. And here we have a screen. And what we will observe is a pattern of a diffraction pattern. So let me have a geometrical consideration here alone. Now, an electron can be projected, say, in these two directions. And let me point this as E, and let me call this as C, and let me take the center as O and this as T. Now, after the passing through this slit, the electron beam spreads. It spreads out. It suffers diffraction, and that's why we have a pattern like that on the screen. And the first minima. So if I assign this as an angle theta, so the first minimum of this diffraction pattern can be given by d sine theta equal to n lambda. Now this d in this case is, of course, it's the width of the slit. And what I do here is that I take this width of slit equal to the uncertainty in the measurement of position. And to replace this d, I would like to write del x sine theta is equal to lambda for n equal to 1. So what we have is we are trying to have Heisenberg's uncertainty principle from the single slit diffraction experiment, and until now I think it's clear that what we have on board. Now, so from this equation, if I have to evaluate this thing, I mean, it's very difficult basically to locate the exact position of the slit at which this the beam of electrons enter the slit. Therefore, the uncertainty in the measurement of its position of the electron beam in this slit, that's considered in the direction perpendicular to the direction of incident beam, should be equal to delta x. That I was telling, that uncertainty perpendicular to the beam that's going in the horizontal direction, and that uncertainty is delta x. So what we have here is delta x sine theta is equal to lambda. Now, talking about the momentum part of this problem. Now, if the electron moves in the direction suppose the electron moves in the direction of EC, right? So what do we expect here? After diffraction, then the momentum of this electron in the direction perpendicular to its initial direction of the electron, that's along this OC. That should be that component of the momentum should be P sine theta. Right? Now, if the electron after diffraction, now if it takes after diffraction, it goes through this direction, ED, right? Now, in this case, the momentum along the perpendicular direction, in this case, will be minus P sine theta. That should be the case. Now, as the electron may be anywhere, it may be anywhere within this diffraction pattern from the angle that can be defined as theta 1 and theta 2. The perpendicular component of this momentum of the electron may be anywhere between minus p sine theta and plus p sine theta. Therefore, the uncertainty that we want to measure, therefore the uncertainty in the measurement of the momentum of this electron along this y direction will be, what will that be? That uncertainty, suppose that is delta p, what will be that? That is going to be p sine theta minus p sine theta. They are vectors, we can understand that. Okay. So we have this kind of situation. So what will be delta p here? So if I take the magnitude, this is p 2p sine theta. And from here, if I already have what delta x is the uncertainty in the measurement of the position along the perpendicular direction, and that is delta x sine theta is lambda. So if I have to write delta x, that is lambda by sine theta, right? So what am I going to get here is I can think of using this p from de Broglie equation. Lambda is h by p, right? So what is p then? This implies this p is h by lambda, right? This p has to be h by lambda. So I can think of using this h by lambda in this equation. So what am I going to get is uncertainty in the measurement of position will be 2 times h by lambda sine theta. So this is my uncertainty in the measurement of momentum. This is my uncertainty in the measurement of the position. So I can multiply the two. So delta x, delta p. Yeah, what will be that? That will be lambda by sine theta times 2h by lambda sine theta. Sine theta, lambda will go. So we'll get delta x, delta p equal to 2h. And which is certainly in agreement with Heisenberg's uncertainty principle. So this way we have arrived to the same conclusion by making use of a single slit diffraction experiment for electrons that are diffracted through this slit, and we are in a position to calculate the uncertainties, the product of uncertainties in the measurement of position and momentum, and the product of the two comes out to be 2h, which is in excellent agreement with the predictions of Heisenberg uncertainty principle.